welcome to today's online demonstration for Chem 1212 Lab at the University of North Georgia. My name is Nikki Driver, and today we are going to be doing the Solutions Lab. The Solutions Lab has 4 parts, and so I'm going to start with part 1 and then go through each of the different parts. Now, part 1 is the only quantitative part of the lab. What that means is it's the only part where we actually care about things like masses, numbers, right, and weight numbers and things like that. And so the reason why we care is because the point of part 1 is to look at a KCl solution and determine what its concentration is. So today we will be looking at KCl solution B. It doesn't say what molarity it is because we are going to figure it out. So I'm going to start with 5 milliliters of KCl, and I'm going to put it in an evaporating dish. And what we're going to do is we're going to heat up the evaporating dish and boil off all the water so that only the KCl salt remains. Now, first thing I have to do is use my mass balance, so I zero it out. And I go ahead and I set the evaporating dish on it. And I say, okay, there's the mass. I write that down. And then I'm going to go ahead and I'm going to add 5 milliliters of my KCl solution right into the evaporating dish. So it's basically just going to look like a puddle of water at the bottom of the evaporating dish. And then I'm going to weigh this. The mass should be higher. If it's lower, you've done something wrong. Alright, so now I have my evaporating dish full of my KCl solution, and I'm going to take it over to my double boiler setup. Alright, so I'm going to take my evaporating dish full of KCl solution and put it on top of a boiling beaker of water. This creates a double boiler, which will have the effect of evaporating off all the water from the KCl solution, leaving just behind the salt. Leaving behind just the salt. Alright, this is what the KCl solution looks like after the water's been evaporated. You can see those lovely little white crystals down there stuck to the bottom of the evaporating dish. So now I can take it off the double boiler and carry it over to the mass balance. Alright, so this is part 2 of the Solutions Lab. We're going to take 3 different solids and look at each of them in 2 different solutions. So our 3 solids are going to be sodium carbonate, naphthalene, and calcium carbonate. And we are going to look at them in water and toluene. So I've already gone ahead and weighed out 0.1 grams of each of our solids. So it goes sodium carbonate, naphthalene, calcium carbonate, and then repeat. Now if you want to know, okay, which one does the first test tube go to, there is table 2 in your lab, and actually has all of them listed in order. So our first experiment here is sodium carbonate, and we're going to put it in 3 milliliters of water. Now this is a qualitative lab. That means the numbers don't really matter. So when I measured out 0.1 grams, I kind of estimated it. And what we're going to do here is we're going to estimate liquids so that we don't have to use a graduated cylinder. So I know that this is 3 milliliters of water. So I'm going to go ahead and fill up my test tube here with about 3 milliliters of water. So I'm going to do that for the first 3, and then the next 3 I'm going to fill out with 3 milliliters of toluene. And then I'm going to put parafilm on the tops of the test tubes so that I can shake them. Alright, cut.
Let's go.
Alright, so we have added the solution to each of these, and now we're going to put parafilm on the top. Parafilm is kind of like a scientist's plastic wrap. It's very stretchy. Stuff's a little bit old. Stretch. And it's kind of sticky. And you can wrap it around the top of a test tube, just like this. Now when you do that, that means that you can put your thumb on the top and shake it up and down, and the liquid can't escape. So I'm going to do this for all 6 of our samples, and then what we're going to do for this experiment is see which ones are soluble and which ones are not. Alright, so in each of these test tubes we have sodium carbonate and water. It's nice and clear. In this one we have naphthalene and water. you can clearly see the naphthalene floating on the top. In this one, we have calcium carbonate and water. You can see some calcium carbonate or chalk there in our water. This is sodium carbonate and toluene. There we go. You can see the sodium carbonate there on the bottom. This is a mixture of naphthalene and toluene, a nice clear solution. And this is a mixture of calcium carbonate and toluene. You'll notice this is a little bit red. When I was shaking them, the permanent marker that marked what number these test tubes were got into my gloves, and that got into my solution. So that is why you should actually use the parafilm to cover things instead of just using gloves like I did earlier. Now for experiment part 3, we are actually going to consider the miscibility of two different liquids. So in test tube number 1 here, we have 2 milliliters of water, and we are going to add 2 milliliters of isopropanol. Let's do so. And mix it up a little bit. You want to mix very vigorously. And you can see that they mix together quite well. Alright, so you can see that they mix together quite well. So that would mean that water and isopropanol are miscible with each other. That means the two solutions actually mix together. So when things are miscible, they mix. When things are immiscible, they do not mix. Now let's look at water and toluene. Here, there's very clearly something that we call an interface. So you can see it's kind of like there's two layers, and the bottom layer of the test tube is separated from the top layer, and that is true, they are separated. So I'm going to shake them vigorously here, and now you can see as the liquids basically recover from the shaking, they actually go and they form that interface again. The two liquids do not mix. That would be what we call immiscible. So our last experiment is going to be isopropanol and toluene. So I've already added the toluene, and now I will add the isopropanol. I'm going to go ahead and shake it. Ooh, this is what it looks like when I'm shaking it. Ah! And now you can see right now it's all cloudy. Alright, so after shaking it, we can see the isopropanol and the toluene. They're kind of foggy. And those are our three solutions. If you forget what they are, then you can just go back to table 3 in your lab, and there's a list of exactly which is in what test tube from left to right. Now, sometimes it can be hard to tell if things are miscible or immiscible, and when I can, because, you know, it's fun and why not, I like to use food coloring. Now, what that does is basically food coloring mixes with water, and if water mixes throughout the entire solution, then that means that there's water throughout the whole thing and the two solutions have mixed. Alright, so let's check it out. Alright, that looks pretty uniform to me. A lovely, nice, deep green. This one, you can actually see some bubbles of food coloring stuck in the toluene. They would not dissolve. And here, you can very clearly see that there's a nice dark green bubble at the bottom. But the solution isn't mixed 50-50, so it's not quite an even split like this guy. This one, it's very clear to see that the water is on the bottom and that toluene is on the top, since the food coloring only mixes with the water. So density-wise, I can say that water is more dense than toluene. Now, if they were miscible, I really couldn't say anything, because if they're miscible, you can't tell. Alright, so for our final experiment, we are going to look at 2 Alka-Seltzer samples, and we are actually going to dissolve them in water and see how long it takes to dissolve. Now, the trick is that one of them we are going to grind up in a mortar and pestle. So basically, we're going to deal with some finely ground Alka-Seltzer tablets and one big chunk of Alka-Seltzer and see which one dissolves fastest. Alright, get your stopwatches ready. Here we have on the left our coarse Alka-Seltzer, and on the right our fine Alka-Seltzer. So we're going to add about 5 milliliters to each of them and see which one dissolves the fastest. Whoop, it looks like the fine is getting an early lead. Even gave the course a little bit more water, and it still turned out to be slower. Now, what is the point of this experiment, you may ask? Well, besides watching bubbles form, the idea is that since the ground up Alka-Seltzer has more surface area, it dissolves more rapidly and the reaction has much more vigor. Right? You saw clearly how the bubbles went almost to the top of the test tube. Whereas the large chunk is still bubbling away. Bubble, bubble, bubble. So the more surface area something has, the faster it dissolves. Alright. Well, that is all 4 experiments.